Director of the Energy Change Institute here at the Australian National University, and I'm joined this evening by Professor Wojciech Lipinski.
Hello.
Before I begin, I'd like to acknowledge the traditional owners of the land on which we meet and also on the airways on which we meet. And I would like to pay my respects to their elders past, present and emerging. So during this discussion this evening, we will have time for you in the audience to ask questions for live Q&A at the end of the audience. If you would like to submit your questions, please use the comment section on YouTube and we will pick up your requests as we go along. So as I said, it's my pleasure this evening to be talking with Professor Wojciech Lipinski. Wojciech works in the Research School of Electrical, Energy and Materials Engineering here at ANU. And he, of course, comes from Warsaw in Poland originally, where he did his Masters at the University of Technology. He then did a PhD at ETH in Zurich, and then moved from there to the United States, to the University of Minnesota, and from there came to the ANU in 2013. Wojciech is a world-leading expert in solar thermal energy, and indeed he leads the solar thermal group here at the ANU. His work concentrates on high-temperature processes, which of course leads to the production of things like renewable fuels, and that'll be the subject of our discussion here this evening. Wojciech, over to you.
Thank you very much, Ken. Hello, everyone. So I'm going to talk today about renewable fuels for aerospace, and I will start with a brief historical survey of the developments in the aviation and space exploration fields. Humans have dreamt of flying since ancient times. We learned at school about the story of Daedalus and his son Icarus. Leonardo da Vinci also was passionate about designing flying objects, and he showed some of these designs in his Codex on the Flight of Birds. As we can see here, one of these designs has a shape that is quite similar to a modern space shuttle, actually. So it is very interesting. Closer to our times, Otto Lilienthal developed gliders, and he tested them successfully. So this was towards the end of the 19th century. The real breakthrough in aviation came with the flight by brothers Wright in 1903, and then the real revolution started. Soon after, during the Second World War or during the Cold War, we had already very powerful large aircraft flying all around the world. Now, the first commercial jet airliner came very soon after the Second World War, which was the de Havilland 106 Comet. And then we had the Concorde, the supersonic jet for passenger transport, and a similar supersonic construction, but for military applications, Tupolev Tu-160, which is in use to the present day. Now, earlier this year, Qantas announced that they retired their Boeing 747 fleet to replace this aircraft, iconic aircraft, with Airbus A380 and Boeing 787 Dreamliner, which are more fuel efficient. And when we look at the history of aviation, we should also remember about the important developments of helicopters, the pioneering work of Arthur Young, which led to the development of the Bell 30 helicopter model, and very soon to the development of many other helicopters. Similarly, the development of rockets is not a very recent story. Actually, rockets were built already during the Song dynasty between the 10th and 13th century, not to transport people, but for military purposes. Konstantin Tsiolkovsky laid foundations for modern aerospace in the beginning of the 20th century, and Robert Goddard, in the other part of the world, tested his first liquid fuel rocket. It took actually less than 40 years for Yuri Gagarin to orbit the Earth in his Vostok 1 spacecraft. And very soon after that breakthrough, the team of Apollo 11 landed on the moon. And then the space race was in full swing. So the first space station was built in 1986. The name was Mir, which is in Slavic languages means peace or world. And this space station ended its existence in 2001, which was related to some problems with supply docking. There was even an accident, but it was replaced by the International Space Station, which is in use to the present day. And its operation and life on ISS can be tracked online. Humans send devices outside our solar system. Our devices, or the human-made devices, landed on our other planets and, of course, in the outer solar system. Now, all these developments have been based on propulsion that relies on combustion. So pistons engines were deployed in aircraft, and majority of modern aircrafts use jets, turbojets, turbofans, turboshaft, and turboprop engines. For rockets, pulse jets were developed, or solid fuel rocket engines, or liquid fuel rocket engines. So there is the whole variety of technical developments built primarily in the 20th century that is now in use, and that is in use in aviation and in rocketry. Now, what are the options beyond combustion? Perhaps you have seen the Solar Impulse 2 aircraft piloted by Bertrand Piccard. Well, it uses an electric motor. Electric propulsion has also been proposed for space exploration, electrothermal systems, electrostatic systems, and electromagnetic systems. Furthermore, for space applications, solar thermal and nuclear thermal propulsion has been proposed, but this is perhaps a little bit still in the, let's say, concept stage. And finally, we also rely on stratospheric balloons for weather monitoring, for communications. So there is a lot happening in the space beyond combustion. Very interesting concepts have been developed, and well, the options are open.
So Wojciech, we've seen, of course, combustion dominate the 20th and early 21st century propulsion systems, not only in aerospace, but also on ground transport. And then, of course, in recent times, we've seen the development of renewable electricity and electrochemical storage technologies, and this has really moved ahead the vehicle propulsion systems that we have on the ground. What do you think will be the prospects for these electricity-based systems in aerospace?
It's of course tempting to think that we can extrapolate the ground-based transportation to aviation based on electricity. There is one major challenge. The storage of electricity is not easy and is heavy. So because of the large weight of the batteries, or perhaps chemical fuels combined with fuel cells, the weight of the aircraft increases. And that requires quite a large surface area of wings to lift. But with large surface area of wings, the resistance against the air increases substantially. So there are challenges. Perhaps the electric propulsion will be a good way to think about for short range flights, but for long range flights, that I think it will always remain challenging, even if very efficient and very light batteries will be invented. To my knowledge, that it will be challenging for long range flights.
Please continue.
Thank you. So commercial aviation has grown to a very large industrial sector. People use airplanes to connect between any part of our planet these days. And there are many flights in operation. Before the COVID-19 pandemics erupted, we had up to 200,000 flights per day, of which almost half, or slightly more than half, were commercial flights. Now, in 2019, there were more than 4 billion passengers transported by air. And this was a twofold increase since 2005. This number corresponded to about 1.5 to 2.5 million passengers in the year instantaneously, which is a medium to large size city instantaneously being up there in the air. Now, kerosene and jet fuel are the basic sources of energy for aviation propulsion, and also in aerospace for some, at least for some stages of the launch of a spacecraft. Kerosene is a mixture of various hydrocarbons, typically C9 to C16. It has, so that means there are between 9 and 16 atoms of carbon and some more atoms of hydrogen in a molecule of such a hydrocarbon. Jet fuel is mainly based on kerosene, but there is no specific chemical formula to define a jet fuel. Jet fuel is defined based on the characteristics of the fuel, and the most widely used commercial fuels are Jet A, mostly in North America, and Jet A1 internationally. Now, the state of the art to produce kerosene and jet fuel is refining of petroleum or synthesis of hydrocarbons mostly from fossil fuels. Now, hydrocarbons are a gold standard of energy carriers because when they are oxidized, they release a relatively large quantity of heat at high temperatures, and unfortunately, the combustion process also leads to the release of CO2, which is the greenhouse gas. Water is also a greenhouse gas, which is produced during combustion, but it will condense, and after some time, it will precipitate, so it is removed from the atmosphere. CO2 will stay in the atmosphere until it is bound by biomass, or it is removed actively by some devices, human-made devices. Now, flying has an environmental impact. Besides those CO2 emissions, which were about 2.4% in 2018 of all anthropogenic emissions, there are also nitrogen oxides, which are detrimental which are a pollutant. Water condensation trails, particulates, and for aircraft using leaded gasoline, there is lead, which is also a pollutant. Now, we also have to deal with noise. Sometimes we have fuel and chemical spills, and in winter at low temperatures, de-icing chemicals are used, leading further to some problems with pollution. For space, the main problem has become the space debris. So there is a lot of waste out there. It is tracked very precisely in the orbit, but there is no cheap way probably to bring it back to the Earth. And that space debris is presents risk to the future space travel and to space station. Now, it is projected that the global jet fuel energy consumption will increase by a factor of 4 for non-OECD countries by 2050, and by about factor of 2 for OECD countries. Most of this growth will come from China, Europe, and Southeast Asia. So definitively, if we are going to use more jet fuel, there will be even more carbon dioxide emissions, and we should address this issue now. Now, are there options to get away, to replace the hydrocarbons? with carbon neutral fuels, or at least to skip the problem of carbon emissions? Well, a straightforward solution that may come to our mind is to use hydrogen everywhere. It is used in space industry. It is a fantastic fuel for rockets, but it is perhaps not the easiest fuel to be used for aircraft. These days, hydrogen is made mostly using electrolysis. If we talk about the renewable energy-based generation of hydrogen. And at low temperature, it can be electrolyzed with quite satisfactory efficiency using mature technologies. At higher temperatures, for the so-called high temperature electrolysis, we still have plenty of R&D going on there, but there is a promise of higher efficiencies. Now, hydrogen is used as a rocket fuel. It was used for stages 2 and 3 for the Apollo 11 rocket. It was also tested on the experimental aircraft Tupolev Tu-155 in the Soviet Union, and recently it was demonstrated as a fuel on the HY-4 aircraft developed by DLR and a Slovenian company Pipistrel. So this aircraft was fueled by hydrogen, which was then used in a fuel cell to generate electricity, and an electric motor was driving the propulsion system. There are other options which are also hydrogen-rich, such as ammonia. Here, hydrogen is bound to a nitrogen atom, and the traditional method to make the ammonia is the Haber-Bosch process, where nitrogen reacts with hydrogen at high pressures and elevated temperatures to produce this energetic chemical. Also, hydrazine contains nitrogen and hydrogen, but this fuel used in rockets and also in some niche aviation applications is highly toxic. I don't believe it will make its way to the mainstream fuel ever, but of course it is used there. And the last option, you may be surprised that I'm showing here hydrocarbons as a carbon neutral fuel. Well, I'm showing it for two reasons. There is a lot of development out there, which is achieved over at least a century, where there is an infrastructure, there are engines that are highly optimized for hydrocarbons, such as kerosene. But of course, we have the issue, if we use hydrocarbons, we emit carbon dioxide. Well, we can produce synthetic hydrocarbons by using carbon bound by biomass or directly captured from the atmosphere.
So it looks like maybe the simplest, at least conceptual way of producing an emissions-free fuel might just simply be to use solar and wind electricity to then use the electric current through water to generate hydrogen and oxygen, and then capture the hydrogen and then use that as a fuel for aviation and aerospace. But that would, of course, produce no carbon dioxide in the process. Are there any disadvantages from going down that pathway?
Well, as I mentioned, in the space sector, actually hydrogen is used there, and it is a great fuel because it has high energy density per unit mass when we use mass as the reference. And mass is everything when we shoot rockets to the orbit and farther away. However, for aviation, there is the negative side of hydrogen shows, and this is the low volumetric energy density. It takes a large volume to store hydrogen, even at very low temperatures. At cryogenic conditions, let's say at 10 Kelvin, for liquid hydrogen, we still deal with a large volume. And we should not forget that there is a container that has to carry this liquid cryogenic hydrogen. So Basically, we equip an airplane with quite a challenging technology, which I think will remain challenging. Hydrogen is a nice clean fuel, but it's not an easy fuel for storage.
Right. And not even bottles of hydrogen in heavy-duty cylinders are going to do the job.
Another issue is with tuning the turbines or engines to be operated on hydrogen. There are examples, for example, the recent SGT 600 turbine that can use in a hybrid mode both kerosene and hydrogen. But for pure hydrogen, there is a change to the combustion process, and there is less experience with using hydrogen as a jet fuel than using kerosene. Also, there is an issue of safety, and so we have much less experience with hydrogen.
Okay, please continue.
Thank you. Now, we have one option that I showed is to make renewable hydrocarbons. And I would like to tell you a little bit how to make these hydrocarbons using solar energy. And in fact, specific form of the solar energy, which is the concentrated solar radiation. In this scenario, we can use high temperature solar heat to process biomass in processes that we call reforming or gasification, and the resulting product is the synthesis gas. Once we obtain the synthesis gas, a mixture of hydrogen and carbon monoxide, we can produce synthetic hydrocarbon fuels using state-of-the-art industrial processes such as the Fischer-Tropsch process. Then we produce the synthetic hydrocarbons such as kerosene, jet fuel. We can use them in the state-of-the-art aviation. We can use the state-of-the-art distribution infrastructure and safety certifications. And then there will be emissions, CO2 and water. They will go to the atmosphere, water will condense, but CO2 will stay there. If we again use biocrops to bound this CO2 from the atmosphere, we will close the carbon cycle, and that way we will have a system where the hydrocarbons are actually carbon neutral fuels, or we can call them solar fuels, because solar energy is used to grow biomass, and solar energy is also used to process that biomass to this high-value liquid hydrocarbon fuel. It's one option. Another option is to directly capture carbon dioxide. So instead of relying on photosynthesis, we can engineer artificial CO2 capture systems and then process that carbon dioxide together with water, again, to produce the synthesis gas, to produce synthetic fuels, to use in the state-of-the-art aviation, to use the state-of-the-art infrastructure, and then to use, again, CO2 capture to close the carbon cycle. So if we put carbon dioxide out there, we have to clean it up. And that fuel will be still carbon neutral. So the core, or the major challenge to realizing this vision is to bound the atmospheric CO2 and then process the carbon using renewable energy to high value products, synthetic hydrocarbon fuels. Now, I'm going to tell you about one specific way how we can do that. Let's imagine we have a solar cavity, very hot cavity, typically at more than 15 degrees Celsius, in which we reduce metal oxides to produce a reduced metal oxide, and this reduced metal oxide can then react with water or with carbon dioxide. As a result, we produce hydrogen and carbon monoxide, while the metal oxide is reoxidized to its initial state and then can be used again in the reduction step. And for that process, many metal oxides have been envisaged, starting from ferrites based on iron oxide, zinc oxide, cerium dioxide oxide, mixed metal oxides, and some others. So I'm showing here one example of a solar thermochemical reactor, a device that is designed and operated to reduce a metal oxide using concentrated solar radiation at very high temperatures. This reactor actually was built and tested, operated at more than 2000 Kelvin. And the reduced metal oxide, it can then be used to split water or carbon dioxide. It's just one example of the quite a broad field called solar thermochemistry. Now, where to take carbon dioxide? We need to split carbon dioxide, but there is no lake of carbon dioxide. There are rivers or lakes of water. Carbon dioxide is in the atmosphere. And unfortunately, it is there at very low concentrations. And I'm saying unfortunately from the thermodynamic point of view. In order to take this carbon dioxide from the atmosphere, we need to pay a large energy penalty. But it is, of course, not desired to keep increasing the carbon dioxide concentration, because that will only make the global warming worse. Now, there are also other sources of carbon dioxide, which are combustion sources, power plants, or industrial sources where based on combustion, or even processes such as cement or lime production. These streams of carbon dioxide are characterized by higher concentration of CO2. It is easier to extract CO2 and then put in, for example, into processes for production of solar hydrocarbon fuels. So I'm going to show you 3 specific examples of technologies that are aiming at direct capture of carbon dioxide from the atmospheric air. The first technology has been developed by the Swiss company Climeworks. In their process, there are 2 phases. In phase 1, the atmospheric carbon dioxide is bound by a sorbent, and then in phase 2, this carbon dioxide is released from the sorbent by heating it, and what we obtain is a pure stream of carbon dioxide. So you can see here the demonstration plant, which is actually the first commercial direct air capture plant in the world, located outside Zurich, and it has been in operation now for quite some time. Another process was proposed by the company Carbon Engineering from Canada, which is based on chemical looping with metal carbonates and with metal hydrides. In that process, we have 2 loops, and they have been implemented in a pilot plant, and the results from the pilot plant were used to build a commercial, or to design a commercial scale reference plant. The third example comes from the United States, and that's the system developed by the group of Professor Klaus Lackner at the Arizona State University, where they have developed a process called moisture swing sorption, implemented in an artificial tree. So there is no source or no fan in the system to blow the air through the tree. The system relies on the natural airflow, or simply wind. And one more example comes here from the Australian National University. We have been working on capturing carbon dioxide from flue gases. As I mentioned, this can be exhaust gas from cement or calcination plants. It can be an exhaust gas from carbonation from plants, power plants based on combustion. In the first, so we have here a 2-step process. In the first step, we bound carbon dioxide with a sorbent material, for example, calcium oxide, and this carbon dioxide is then released from the sorbent in the second step, which is then powered or driven by concentrated solar radiation. We obtain a pure stream of carbon dioxide. To demonstrate this process, we have developed a solar thermochemical reactor, which is about to be tested in our high-flux solar simulator here at the ANU.
Very good. So I understand that this direct capture process takes a lot of energy. It's a very energetically costly process. And maybe that's the price we have to pay for making these hydrocarbon fuels. But doesn't that mean that biomass might be the more promising route, even though you've got limitations like land and water availability and these sort of things? So what are the pros and cons of these two different ways of realising these hydrocarbon fuels in a sustainable manner?
Yes, so as you have mentioned, when we follow the biomass route, biomass does a nice job. It bounds atmospheric carbon dioxide and it reduces it in the same step. So there is no less energy needed to process biomass than to process raw carbon dioxide. At the same time, there is an increased demand for water, and in countries like Australia, that can be a challenge. It would require probably massive development of desalination technologies. Australia has a long coastline, so that's feasible. Then biomass for energy purposes or biocrops will compete with the food crops. And in some parts of the world, that's already a land limitation, a significant land limitation,
Right.
also impacting the natural environment. Now, when we talk about the artificial about the artificial ways to capture the atmospheric carbon dioxide, there is a promise of achieving much higher efficiencies than the efficiency limited by the photosynthesis process. And that may in the future actually lead to significant cost reduction. We already have these first commercial plants, but I think there is much more potential to basically improve, optimize, and at some point we will see competition between biomass-based approaches and CO2 capture-based approaches, which is healthy for the development of the field.
Indeed, yes, yes. Please continue.
Thank you. Now, I would like to show you an example of a specific development coming from Europe. This is a process developed by a consortium of ETH Zurich in Switzerland and the two spin-off companies, Climeworks, which I already mentioned, and another company called Synhelion. So this consortium developed a complete process, a so-called solar refinery, where the carbon bound from the atmospheric air, as well as water, using solar energy or waste heat, is then used in a solar reactor to produce hydrogen and carbon monoxide, the components of the synthesis gas I already mentioned previously. So using the syngas, we can now produce the liquid hydrocarbon fuels. We can power aircraft, traditional aircraft, and then we close the cycle again by capturing carbon dioxide and water from the air. So capturing water from the air is an interesting step here because solar energy exists is abundant, for example, in arid or desert areas where there is not that much water. If we want to produce fuels there, that may be one of the viable solutions. So the process developed by this consortium is based on a metal oxide called cerium dioxide. It is a two-step process with the solar reduction step and the second oxidation step, which doesn't require solar energy input. In fact, there is some waste heat coming from the second step, which is recycled to improve the process efficiency. Now, the team developed a solar reactor prototype. First, it was a 5 kilowatt solar reactor prototype where the cerium dioxide is shaped in form of a porous structure, which we call the reticulate porous ceramics. And they implemented this reactor in tandem with the second reactor on a parabolic dish with a movable mirror, so that when the one reactor realizes the reduction step, the second reactor realizes the oxidation step, and the process is continuous, or quasi-continuous at least. After this first demonstration, which happened on the roof of mechanical engineering at ETH Zurich, the team scaled up the reactors, the technology, to the power of 50 kilowatts, and the reactors were tested on a solar tower at Imdea Energy in Madrid. Now, I would like to change the topic slightly now, and I would like to show some developments coming or in progress here at the ANU. So at the ANU we have the group of students called ANU Rocketry. It was founded in 2018 to compete in the Australian Universities Rocketry competition, and they had the first rocket launch in 2019. They won on the second place in flight performance in that competition and third place overall. Now they are going higher, so while the first rockets went to 10,000 feet or about 3 kilometers, now they are aiming at 10 kilometers. And in parallel, they are developing a liquid fueled rocket engine, which will be running on a biofuel. And the ultimate goal is to go to space, to be the first Australian university to send a rocket to space. Now, here I'm showing their recent development, which is a three-dimensional 3D printed test engine. This engine will be powered by sustainably sourced bioethanol, and it is meant to be reusable. So the students want to demonstrate here that it is possible to basically develop a rocket engine technology which is of non-astronomical price, let's say, and with engines that are reusable. This is important because it will reduce the amount of debris or waste if it's implemented for real space applications. So if you have any questions about the developments by the ANU Rocketry team, please contact them directly. I'm sure they will be happy to follow up with any further information. So I would like to thank you for your attention, and I would like to thank also my students, collaborators, and colleagues around the world who have been working in this field. And a lot of progress has been achieved, especially in the last decade. So it's quite interesting.
Yes, absolutely. And, clearly there's a lot happening in the way of innovation in this area. What do you see as the special advantages that Australia might have, the comparative advantages to develop a solar fuel aerospace industry?
Australia is a very interesting case. So the number one factor is Australia's geography. Australia has rich solar resources, vast land, where these solar resources can be basically captured, air, and where the carbon dioxide can be also captured on that vast land area. Australia also has a long coastline, which I mentioned already, which means the country has access to seawater, which can be desalinated to provide hydrogen atoms to those solar fuels. And the most important factor here is actually that Australia has the human capital, and I believe this is the key factor to engineer the future solar economy. When we look at the technicalities of Australia as a land of resources, so I want to give a number. If we build a solar plant operating with an efficiency of, let's say, 20%, then it is sufficient to cover an area of 600 by 600 square kilometers with solar collectors to supply all our energy needs for the entire civilization, not just fuels. And Australia has more than one such 600 by 600 square kilometers square.
Indeed.
So there are indeed great opportunities here, as well as in some other parts of the world with good similar conditions.
Yeah, but I guess here we have this wonderful circumstance where we have the coincidence of great solar energy long coastlines, good hydrogen production opportunities, and a very highly skilled, highly educated population to take advantage of these things.
And in addition, the infrastructure in this country is quite advanced, so it won't take that much to basically not only switch Australia's economy to the solar economy, but to become a solar powerhouse for the entire world.
Indeed, and we have great experience with very large-scale commodity export projects that we could just simply turn around and base a new export industry on renewable energy sources.
Indeed.
Great. Well, that's a very interesting perspective then on the prospects for Australia to contribute as a renewable energy powerhouse, and particularly in the area of renewable fuels for aerospace. So now maybe we have the opportunity to take some questions from the audience. And indeed, as we mentioned before, just simply put your questions on the YouTube channel, and we can start to see them on the screen. So let me see, we've got some questions coming up already. So here's a question from Sonia, who wants to know, how does growing the sustainable aerospace fuel sector improve national energy security and economic prosperity? So I guess she's thinking of things like, how do we wean ourselves off the supply chains of traditional fossil fuels and this sort of thing?
That's an excellent question, in fact. Growing the domestic aerospace fuel sector will eliminate the risks, or at least mitigate some of those risks associated with transportation of hydrocarbons from distant parts of this world. These hydrocarbons are processed in yet other places in the world, and if there is an interruption to the supply, let's say using ships, large tankers, then the whole country will be in jeopardy, and the domestic storage capacity is not that large for the case of interrupting foreign fuel supplies.
Yes, and this means that well, countries that are well endowed in renewable resources can more or less become self-sufficient, whereas at the moment we rely on these supply chains around the world. People worry about ships travelling through the Straits of Hormuz, this sort of thing.
Exactly.
And maybe in the future we'll have an even happier and more secure world as a result. Exactly.
Diversifying the sources of fuels, I think, will make the world much more secure and safe.
Yes, okay. So there's a question here from Daniel. In that case, what will it take to make Australia a global leader in renewable fuels? What are the key things that we need to do? I mean, we've just seen the government talk about a technology investment roadmap. Are there elements of that are particularly important for the renewable fuels side of things? Or are there other things that we need?
So I believe that technology is one important enabling factor, but of course there is a long way from existing technologies or future technologies to mass-scale commercial deployment. Economics is an important factor, and now the governments can help here by basically developing policies around so that will favor these developments. Of course, it's a complex situation, and while investing into new technologies is desired, over-investing in a short term may also lead to some other problems, because we are talking about a massive switch from fossil fuels to renewable fuels. It's important to maintain stability in the developments. It's important to maintain inclusion so that these developments happen with participation of the entire society.
And we've seen already that the government in the technology investment roadmap has released 5 priorities, and one of those is actually hydrogen, which we've talked about as being a core element of this renewable fuel production process. So if, let's say, this achieves some degree of momentum as a result of this roadmap, do we need to add other priorities to get the actual renewable fuel side of things in a competitive and productive phase.
So the focus on hydrogen is an important step, of course. We have seen that even hydrocarbons contain a lot of hydrogen. So if we want to make them synthetically, we need hydrogen. Now, hydrogen is not taken out of thin air unless we work on water capture from the air. But I think a more promising route would be to consider desalination, mass-scale desalination, to not negatively impact natural reservoirs. Basically, using large quantities of water may lead to some other environmental issues. We don't want to go there.
No.
And carbon capture, especially some technologies aiming at carbon capture from the air, are also necessary if we want to pursue further the route of renewable hydrocarbons. So we may think of reusing in a short term carbon from flue gases or those industrial sources where CO2 is a waste, but this will only reduce the rate of emissions, not eliminate it. If we want to create a true renewable carbon neutral economy, a fuel economy, we need to also think about investment into direct air capture.
Right. So in the process of changing our industrial systems from ones that are producing carbon dioxide in flue gases to ones that don't, we do have the opportunity to take advantage of the high concentration of CO2 in those flues. But as you say, in the long term, that's a process that will probably disappear anyway as we move to more sustainable methods of production. And the other thing to consider is the energy required to do all of this. So with the desalination, it's actually not that much of an energy cost. It probably only amounts to maybe 1% or 2% of the total hydrogen energy production costs. But things like direct air capture from the atmosphere, that's going to be reasonably energy intensive, is it not?
It is true. And we don't want to arrive at high concentrations of carbon dioxide in the atmosphere. That would make basically the process easier technically, but it is a disaster. It could be a disaster for the whole planet. We don't want to go there. So the penalty for capturing the carbon dioxide is basically the penalty of cleaning up what we put into the atmosphere already.
Yeah.
And there is no way. If we want to develop a sustainable system, we have to invest into these technologies.
Yes. So we've talked about the technology roadmap a little bit already. There's a question for Irene. What is the Commonwealth doing to support the development of these renewable fuels at the moment? Is there a program that will enable this to be funded? Should there be one? Where would we be looking for this investment to come from?
So at the, let's say, research scale, there are indeed existing research programs. I can name some examples. One of them is the program from the Australian Renewable Energy Agency, which is the Australian Solar Thermal Research Institute. And within that institute, we do investigate solar fuels using the thermochemical routes, which I mentioned briefly in my presentation. But there are also other government-funded programs through the Australian Research Council, which are not topic-specific, but of course we researchers keep applying for grants and make use of this funding to advance the technology. An important factor is industrial engagement here. We are talking about research and development that aims at commercial outcomes. And in Australia, it's extremely important to proceed with participation of industry. It's an opportunity to engage even mining companies, mining industry, or energy companies, domestic companies, which may not be focused on renewable fuels these days, but that will give them engagement in renewable fuel research will give them an opportunity to switch the business model from fossil-based to the renewable-based. And there are programs sponsored by the federal government, such as the ARC linkage programs, where participation, co-research between academia and industry is highly encouraged.
Okay. So we have a question from Ed here, who is mentioning what you said about the removal of space junk, and the fact that this is a serious problem for, the aerospace industry generally. So is there a link between the prospects for renewable fuels and removal of space junk? Do we need to send lots of rockets up? Can we do this sustainably? These sorts of questions.
It's a challenging task to remove the space junk. It's diluted out there. It's flying on stable orbits, but to bring it back, I have seen various technical concepts basically to filter it out and bring down to the Earth. I have read about works by economists that if we have some global space debris tax, similar to the previous carbon tax ideas, these debris will be brought to the Earth very quickly, because we should never doubt in human creativity, right? The link between the renewable fuels and the space debris is perhaps via the reusable rocket engines. So if we think, if we work on those sustainable rocket engines that we bring back, and that will to the Earth, well, we will reduce the amount of space waste in the future. But I'm not sure if that directly helps to remove what we already put out there on the orbit, I'd say.
And of course, we've been talking here about being renewable and sustainable and all this sort of thing. So I guess there's a question about, what's happening to the atmosphere then with renewable fuels. So, for example, hydrogen. I mean, there's no hydrogen normally around because it's incredibly light. It's disappeared from the Earth a long time ago. What we have is often stored underground in caverns, or it's been confined for a long time. So let's say this comes out through these processes that we are talking about, and we accidentally release some in the escaping gases from these production processes. Is there a risk of having this hydrogen in the atmosphere in terms of changing the atmospheric chemistry, and maybe that changes, for example, the ozone layer and these sorts of issues?
Indeed, there are risks of basically initiating some photochemistry in the upper layers of the atmosphere. So if we rely on hydrogen as a fuel for aerospace, and there are leaks out there, well, it will end up in those photochemical reactions quite quickly. But even if it is released, as you mentioned, at the ground level, it's a light element, and it goes to the upper part of the atmosphere where we have more intense UV light and photochemistry. Basically, there is photochemistry that leads to reactions that I believe may be not desired to have. So hydrogen is a very interesting chemical. I think it's a fantastic chemical as an intermediate material to work with. I'm a little bit more skeptical when we talk about hydrogen as an end-use fuel that is distributed in broad networks, put in every vehicle and in every end-user application, where sometimes it's hard to control its presence. And so probably we will see more discussion related to this topic, because the hydrogen economy is growing. We have more and more hydrogen generated out there. And the problems, if they are really important, they will be clear.
Yeah.
They will be clear.
Yeah, so more opportunity then for research. So we've got another question here. So let's say for our younger audience, if you're a student out there and you're interested in pursuing a career in renewable energy topics like this, what would you say would be something that would be prospective to get into in say years to come?
Oh, actually, this is such a broad and multidisciplinary topic that I can I would not set any boundaries.
Right.
But of course, I'm a technical person. I'm an engineer with some background in science and technical subjects, and I like working on technology aspects. But of course, we have social aspects, economic aspects, law and policy, legal and policy. And if someone likes politics, perhaps that will be the most impactful career,
Indeed.
possible career to make a global change. Because even if the technology will exist, it may not make it easily to the mainstream without those measures, political measures, to help, at least in the initial stage, to set up the solar economy.
Indeed, and the international trade in things like hydrogen or ammonia or renewable fuels generally requires a whole framework to be set up to make it work. You've got to have the regulatory process in place. If you're worried about the amount of carbon that's contained in the product that you're shipping, you've got to be able to certify it was produced renewably and sustainably. All these sort of things come into play. So, like you say, many disciplines contribute, and actually some of the really tough problems. And I'll give a plug here for the Energy Change Institute at ANU. We're involved in this program called Zero Carbon Energy for the Asia Pacific, where we're trying to do the research underpinning a transition to a renewable energy export future. A lot of the problems we're looking at here are between and across the various disciplines, and we need people with economics and engineering understanding. We need people with regulatory and scientific understanding. So I think there's many opportunities for people in all disciplines to contribute to these exciting new topics.
I totally agree.
Good. Okay, let's see. We've, I think, covered most of these. There's a question, though, about, we're talking about future students. So let's talk about past students like you and me. So the question actually comes from Jim, and Jim asks, how did we both become involved in this kind of research? So maybe Wojciech, you can kick off.
Well, I have worked with a number of people who basically decided to change the focus of their career in the second part of their life. Some of them came from the IT industry, some of them came from the traditional energy sector. So I think changing is always an opportunity. For example, here at the ANU we have offered master's programs, which are not perhaps aiming at the fundamental basic education, science education in the field, but they are broader programs and give some tools to and time to think what is good to select for the second stage of the career. And working in renewables doesn't mean that some existing career needs to be changed. Maybe there is some new flavor, new adjustment, like people working in IT may think of how IT or computer science can be used to make the field of renewable energy more effective. And we have such examples here at ANU, for example, where the grids are modeled with powerful computational facilities, or energy storage problem is solved with basically through computational modeling, which is a formidable task when applied at a scale of energy systems. We are not talking about one device in one particular location. We are talking about national economies and in the future interconnected networks around the world. So that's a specific example for the IT sector. And of course we could go from sector to sector and identify different opportunities, what can be added to the existing knowledge, to the existing career paths. I'm happy to always to receive any if somebody contacts me, I'm happy to give an advice, specific advice within my competence area.
So in your particular case then, have you experienced this shift as you progressed through your career to move from an area that you started out with, maybe doing your PhD, into something that's maybe slightly different and takes you in a new direction?
Yes, I have actually experienced several shifts in my
Right.
career. So my master's degree was in environmental engineering. Then I moved towards applied thermal sciences, but basically now I'm focused on solar thermal energy and thermochemistry. Why? My undergraduate degree was not in chemical engineering. I studied this as I moved on with my research and work.
And now you're in the renewable fuel space as well.
Exactly.
Yeah.
And even touching aerospace.
Indeed, of
where
course.
I have never studied aerospace at school.
Yeah. And I've got a similar story. I'm a physicist as well, a technological and technical person. But over time, I saw around me the development of the energy shift in the world's energy systems. And with my colleagues who work in the development of new energy technologies, I became interested in this area. And 10 years ago, founded the Energy Change Institute at the ANU, which is now an organisation with over 300 researchers, including PhD students. We do everything from the fundamental development of new energy technologies all the way through to the regulatory and economic and policy aspects of implementing energy change. So that's been a transition for me as well.
That's a great example.
Very good. Well, I think this has been a really interesting discussion this week, the third of our topics in Space Week, and this particular discussion around renewable fuels for aerospace, I think, is taking us into the future to a more sustainable world in which space becomes a light touch, if you like, on the planet and helps us to achieve a much more sustainable future. So thank you, Professor Lipinski, for your insights, and thank you everybody for listening.
Thank you very much.